Alright, so we're going to be going over inclusion and exclusion. And so, of course, we start with the original formula, which is we're figuring out the cardinality of all the unions, right? We're figuring out the entire thing, essentially, this entire Venn diagram. So the way we're going to do that is we consider each part, right? A or B or C, we're going to need A in there, because otherwise, like, how are you going to get A? And so we're going to count this part once, this part once, this part once, and this part once, right?
Yep.
Now we're going to need B also, because we're going to need B also. We count this part once, this part once. But now we see some overlap, right?
Yep.
Because we know that A and B overlap in these two areas, but because we're only including B, we're still going to be counting this twice, still going to be counting this twice. And so now we need C, of course. And so we're going to count this once, this twice, and this 3 times.
Yep.
And so we have an issue here, because we have a bunch of overlap, and so this isn't going to give us our result. It's going to give us a much greater result. So in order to deal with these overlaps, we're going to be subtracting out the intersections. And so, so let's start with A intersect B, right? So can I just have a volunteer, like, which parts are A intersect B, right? Which two? Just mention it. Yeah, like there's
that
one more.
N?
Yeah, there's one more. Wait, point again? Sorry.
No, the 3.
Yeah, the 3, right? And so when you subtract out A union B, we're going to get rid of this part, so we're only going to count it once now.
Once.
And now we're only going to count this part twice. And so we're going to do the exact same, where we're going to say A intersect C. And so the intersections are these two. So we're going to make this 1. We're going to make this 1. Now we're going to subtract out B intersect C. This will become 1. Now this becomes 0. And so, can someone tell me what we should do to make sure that we're counting this part once?
Or we count all of them together.
Yeah, exactly.
All
right?
the intersections together.
And so we're gonna count exactly. We're gonna count all the intersections, right? And so now we're counting this part once.
Oh my god.
And so now you get your solution where we count each part exactly once, and so there's no overlap. And so this is your final solution. Now, in terms of like when you're using inclusion and exclusion, a key component in it is that you actually have a greater universal set S, right? Where S is like in the divisibility question, where you have like N equals like from like 1 to 5. I don't know the actual numbers. I'm just making them up. 536.
Yeah.
A is equal divisible by 2 or whatever. B is equal to divisible by like 6 or 7. I don't actually remember the numbers. 5, right? And so your universal set, your S, is going to be all 536 numbers. So here, S is equal to 536 numbers. Your A is equal to, your A is going to be the exact same. All the stuff that's like divisible by 2, divisible by whatever, by divisible by whatever. And so your solution to this question is really S minus that, right? The inclusion exclusion of all A, B, and C. And so, yeah, it's basically like whatever the solution for that problem was. But I mean, you can generalize this to any inclusion exclusion problem, right? Where you have some subset of like all the numbers, and then you subtract out all the unions of like whatever conditions that you're trying to figure out.
Right.
So yeah.